statement "the higher the voltage, the higher the current" is generally true when we are talking about a fixed resistance. This relationship is described by Ohm's law, which is often written as I equals volts divided by resistance, or I equals V over R. This equation tells us that if the resistance stays the same and we increase the voltage, the current will increase proportionally. Similarly, if the voltage stays the same and we increase the resistance, the current will decrease. However, the situation changes when the power remains constant and the resistance is allowed to vary. In your example, the load, which is 5000 watts, is kept constant while the voltage is changed from 220 volts to 110 volts. When power is constant, the relationship between voltage and current is inverse, meaning that if the voltage decreases, the current must increase to maintain the same power level. This is because power, P, is equal to voltage, V, multiplied by current, I, so P equals V times I. If we rearrange this equation to solve for current, we get I equals P over V. This form of the equation makes it clear that if power P is constant and voltage V decreases, then current I must increase to compensate. In your example, when the voltage is 220 volts and the power is 5000 watts, the current is 5000 watts divided by 220 volts, which equals 22.72 amps. When the voltage is reduced to 110 volts while maintaining the same 5000 watts of power, the current becomes 5000 watts divided by 110 volts, which equals 45.45 amps. As you can see, the current is higher at the lower voltage to maintain the constant power. The key to understanding this is recognizing that the resistance of the load is not constant in this scenario. When you change the voltage while keeping the power constant, the resistance changes as well. We can calculate the resistance in each case using the formula R equals V squared divided by P. Firstly, for the 220 volt case with 5000 watts, the resistance is 220 volts squared divided by 5000 watts, which equals 9.68 ohms. Secondly, for the 110 volt case with 5000 watts, the resistance is 110 volts squared divided by 5000 watts, which equals 2.42 ohms. Notice that the resistance is lower when the voltage is lower. This lower resistance allows more current to flow at the lower voltage while still maintaining the same power. In summary, the statement "the higher the voltage, the higher the current" is only true when the resistance remains constant. When dealing with constant power loads, the relationship between voltage and current is inverse, and the resistance changes accordingly. So, if you are looking at a device with fixed resistance, increasing the voltage will increase the current. But, if you are looking at a load that consumes a fixed amount of power, decreasing the voltage will increase the current. It's important to consider whether resistance is constant or variable to determine the relationship between the voltage and the current. Now, let's delve into the mathematical relationships a little deeper. Ohm's law, in its fundamental form, is volts equals current times resistance, or V equals I times R. This equation shows the direct proportionality between voltage and current when resistance is constant. However, in many practical applications, we are more concerned with power. Power is the rate at which energy is transferred or used. It is measured in watts. The equation for power is P equals V times I, where P is power, V is voltage, and I is current. This equation can be rearranged to express current in terms of power and voltage, which gives us I equals P divided by V when power is held constant. As in your example with the 5000 watt load, this equation reveals the inverse relationship between voltage and current. If the voltage decreases, the current must increase proportionally to maintain the same power. Conversely, if the voltage increases, the current must decrease. The resistance of the load in your example is not a fixed value. Instead, it changes depending on the voltage applied to maintain the constant power. The relationship between resistance, voltage, and power is given by the equation R equals V squared divided by P. This equation can be derived from Ohm's law and the power equation. From this equation, we can see that if power P is constant, the resistance R is proportional to the square of the voltage V. Therefore, if the voltage is halved, the resistance is quartered. In your specific example, when the voltage is 220 volts and the power is 5000 watts, the resistance is 220 volts squared divided by 5000 watts, which equals 9.68 ohms. When the voltage is reduced to 110 volts while maintaining the same 5000 watts of power, the resistance becomes 110 volts squared divided by 5000 watts, which equals 2.42 ohms. The resistance at 110 volts is 1/4 of the resistance at 220 volts, which demonstrates the relationship R equals V squared divided by P. It's also important to consider the implications of these relationships for electrical safety and circuit design. When dealing with constant power loads, it is essential to ensure that the wiring and circuit components are properly rated for the expected current. If the voltage decreases, the current increases, and if the circuit is not designed to handle the higher current, it could overheat and potentially cause a fire. Therefore, it is always recommended to consult with a qualified electrician or electrical engineer when designing or modifying electrical circuits. In summary, the statement "the higher the voltage, the higher the current" is true only under the condition of constant resistance. When power is constant, the relationship between voltage and current is inverse, and the resistance changes accordingly. It's important to understand these relationships to properly analyze and design electrical circuits. When analyzing electrical circuits, it's important to consider all the variables involved, including voltage, current, resistance, and power. In many cases, one or more of these variables may be held constant while others are allowed to vary. By carefully analyzing the relationships between these variables, you can gain a better understanding of how the circuit works and how it will behave under different conditions. Let's consider a few real-world examples to illustrate these concepts. Firstly, imagine an electric heater rated at 1500 watts. This heater is designed to provide a constant amount of heat regardless of the voltage applied to it. If the heater is connected to a 120 volt circuit, it will draw a certain amount of current. However, if the heater is connected to a 240 volt circuit, it will draw less current to produce the same amount of heat. This is because the power remains constant at 1500 watts, and the voltage and current are inversely proportional. Secondly, consider a power supply for an electronic device. The power supply is designed to provide a constant voltage to the device, regardless of the current drawn by the device. As the device draws more current, the power supply will automatically adjust its output to maintain the constant voltage. In this case, the voltage is constant, and the current and power are directly proportional. Thirdly, think about a simple resistive circuit with a fixed resistor connected to a variable voltage source. As the voltage is increased, the current through the resistor will also increase, and the power dissipated by the resistor will increase as well. This is a classic example of Ohm's law in action, where the resistance is constant, and the voltage, current, and power are all directly related. It's also worth noting that the relationships between voltage, current, resistance, and power can be affected by other factors, such as temperature and frequency. For example, the resistance of a resistor can change with temperature, which can affect the current and power in the circuit. Similarly, the impedance of a capacitor or inductor can change with frequency, which can also affect the current and power in the circuit. Therefore, it's important to consider all the relevant factors when analyzing electrical circuits. Now let's address the concept of impedance. Impedance is the opposition to the flow of alternating current, AC, in a circuit. It's similar to resistance in a direct current, DC, circuit, but it also takes into account the effects of capacitance and inductance. Impedance is represented by the symbol Z and is measured in ohms. In a purely resistive circuit, the impedance is equal to the resistance. However, in a circuit with capacitors or inductors, the impedance is more complex and depends on the frequency of the AC signal. The impedance of a capacitor decreases as the frequency increases, while the impedance of an inductor increases as the frequency increases. The relationship between voltage, current, and impedance in an AC circuit is given by Ohm's law, which can be written as V equals I times Z, where V is the voltage, I is the current, and Z is the impedance. This equation is analogous to Ohm's law for DC circuits, but it uses impedance instead of resistance. The power in an AC circuit is also affected by the impedance. The average power dissipated in an AC circuit is given by the equation P equals V times I times the cosine of theta, where P is the average power, V is the voltage, I is the current, and theta is the phase angle between the voltage and the current. The phase angle is determined by the impedance of the circuit and represents the difference in timing between the voltage and the current. In a purely resistive circuit, the phase angle is zero, and the power is simply V times I. However, in a circuit with capacitors or inductors, the phase angle is non-zero, and the power is reduced by the cosine of the phase angle. This is because capacitors and inductors store energy rather than dissipating it, so they don't contribute to the average power. Understanding impedance is crucial for analyzing and designing AC circuits, especially those that operate at high frequencies. It's also important for understanding the behavior of transmission lines, antennas, and other components that are used in communication systems. Furthermore, let's look at power factor. Power factor is a measure of how effectively electrical power is being used in an AC circuit. It is defined as the ratio of real power to apparent power. Real power is the power that is actually used to do work, while apparent power is the product of the voltage and current, regardless of the phase angle between them. Power factor is expressed as a number between 0 and 1. A power factor of 1 means that all the power is being used effectively, while a power factor of 0 means that none of the power is being used effectively. In a purely resistive circuit, the power factor is 1. However, in a circuit with capacitors or inductors, the power factor is less than 1 because some of the power is being used to charge and discharge the capacitors or inductors rather than doing useful work. A low power factor can lead to several problems, including increased energy costs, reduced equipment capacity, and voltage drops. Therefore, it is important to maintain a high power factor in electrical systems. There are several ways to improve power factor, including adding capacitors to the circuit to compensate for the inductive loads and using power factor correction equipment. Power factor correction equipment typically consists of capacitors and inductors that are carefully selected to counteract the effects of the inductive and capacitive loads in the circuit. By improving the power factor, you can reduce energy costs, increase equipment capacity, and improve voltage stability. Power factor is an important consideration in electrical systems, especially those with large inductive loads such as motors and transformers. By understanding power factor and taking steps to improve it, you can save energy and improve the performance of your electrical systems. Additionally, the National Electrical Code, or NEC, provides guidelines for electrical installations to ensure safety. The NEC covers various aspects of electrical wiring, protection, and equipment. It is updated regularly to reflect changes in technology and best practices. The NEC contains numerous tables, such as NEC Table 310.15b16, which provide ampacity ratings for conductors. Ampacity is the maximum current a conductor can carry continuously under specific conditions without exceeding its temperature rating. The NEC also includes requirements for overcurrent protection, such as circuit breakers and fuses. Overcurrent protection devices are designed to protect conductors and equipment from damage due to excessive current. The NEC also specifies requirements for grounding and bonding. Grounding is the connection of electrical equipment to the earth, which provides a path for fault current to flow back to the source. Bonding is the connection of metallic parts of electrical equipment to create a low impedance path for fault current. Grounding and bonding are essential for safety and help to prevent electrical shock. The NEC also covers other topics such as wiring methods, equipment installation, and hazardous locations. It is important to follow the NEC when installing or modifying electrical systems to ensure safety and compliance with regulations. Licensed electricians and electrical engineers are trained to interpret and apply the NEC.